The sun is not eternal. That sentence carries a weight most people never stop to feel. We wake up to it. We build our calendars around it. Every civilization in human history has oriented itself, spiritually, architecturally, agriculturally, around this single object burning at the center of our solar system. And yet the sun is running out of fuel. It has been doing so since the moment it was born, 4.5 billion years ago. Every second, every minute, every year that passes, it burns through a quantity of hydrogen so staggering that the human mind has no natural frame of reference for it. 600 million metric tons of hydrogen are fused into helium inside the sun's core every single second, not every hour, every second. To put that into something your body can understand, if you stacked every skyscraper on Earth, every one of them, from the Burj Khalifa to the Empire State Building, their combined mass wouldn't come close to what the sun burns through in a fraction of a heartbeat. And it has been doing this continuously, without pause, for longer than complex life has existed on this planet. The sun is not a fire. This is the first misconception that must be dismantled, because fire, as we know it, is a chemical reaction. Carbon combining with oxygen, releasing energy as heat and light. A campfire burns. The sun does not burn. The sun fuses. Deep inside its core, under pressures 15 trillion times greater than the atmospheric pressure at sea level on Earth, and at temperatures reaching 15 million degrees Celsius, hydrogen nuclei are forced so close together that they overcome their natural electromagnetic repulsion and merge into helium. In that merging, a fraction of their mass is converted directly into energy according to the most elegant equation in the history of science. Energy equals mass, multiplied by the speed of light squared. The speed of light is approximately 300,000 kilometers per second. Square that number. The energy released from even a tiny loss of mass is almost incomprehensible. That process, nuclear fusion, is what makes the sun shine. And it has a limit. The sun began its life with an enormous reservoir of hydrogen fuel. Roughly 71% of its total mass at birth was hydrogen. But it has been spending that reservoir continuously. Right now, today, the sun is approximately halfway through its main sequence lifetime. It has been a stable hydrogen-fusing star for about 4.6 billion years. It has roughly another 5 billion years left before the hydrogen in its core is exhausted. 5 billion years sounds like infinity. It isn't. It is a number with an end. A real, physical, non-negotiable end that is written into the laws of nuclear physics and stellar evolution. Laws that apply to every star in the observable universe without exception. What no one tells you, what gets lost between the "don't worry, it's 5 billion years away" reassurance, is that the sun is not waiting for the end to start changing. It is changing right now. Today, the sun is approximately 30% more luminous than it was when Earth first formed. 30% brighter. That is not a dramatic leap by stellar standards, but over geological timescales, it has had enormous consequences for the evolution of life on this planet. And it will have far more dramatic consequences in the far future, long before the sun actually dies. The slow brightening of the sun is one of the most underappreciated facts in all of planetary science. Astronomers call it the faint young sun problem, and it reveals a paradox at the heart of Earth's history. When the sun was young, it was significantly dimmer. Simple physics tells us that a younger, dimmer sun should have left early Earth frozen solid, a snowball planet incapable of supporting liquid water. And yet the geological record is unambiguous. Liquid water existed on Earth's surface as far back as 4 billion years ago. Life emerged, oceans formed. Something kept the early Earth warm enough despite receiving considerably less solar energy than we receive today. The answer lies in greenhouse gases. The early Earth's atmosphere was rich in carbon dioxide and methane, concentrations far higher than anything in the industrial era, and those gases trapped enough heat to compensate for the sun's dimness. Over billions of years, as the sun gradually brightened, Earth's atmosphere evolved in tandem, drawing down carbon dioxide through geological and biological processes to keep surface temperatures in a livable range. It was not design. It was not luck. It was the slow, blind, continuous negotiation between a warming star and a living, geologically active planet. That negotiation has limits. At some point, not in 5 billion years, but far sooner, the sun will become too bright for Earth's natural feedback systems to compensate. Current models in stellar and planetary science suggest that within approximately 1 billion years, solar luminosity will increase to the point where Earth's oceans begin a runaway evaporation process. Water vapor, itself a potent greenhouse gas, will amplify the warming. The oceans will boil into the upper atmosphere. Ultraviolet radiation from the sun will break apart water molecules at altitude. Hydrogen atoms, being so light, will escape Earth's gravity entirely and drift into space. The water will not return. Earth will begin its transformation into something resembling the surface of Venus today, a scorched, pressurized, waterless world where the surface temperature climbs high enough to melt lead. 1 billion years. It sounds distant. In cosmic terms, it is not far. The entire history of complex animal life on Earth, from the Cambrian explosion to this moment, spans only about 540 million years. 1 billion years is less than twice that. The window in which complex, water-dependent life can exist on Earth is not open-ended. It is closing. Slowly, almost imperceptibly by any human timescale, but closing with the mathematical certainty of a star following the laws it cannot break. And this is only the beginning of the story. The sun's death, the actual end, is a far more violent and extraordinary event than a simple fading. It is a transformation, a swelling, an expansion of almost inconceivable scale. The sequence of events that follows hydrogen exhaustion in the sun's core will redefine the architecture of this solar system entirely. The inner planets, Mercury, Venus, Earth, exist today in orbits that were established when the sun was a fraction of its eventual size. Those orbits may not remain safe. Whether Earth survives the sun's final transformation is not a settled question. The answer depends on orbital mechanics, mass loss rates, tidal forces, and feedback effects that astronomers are still working to model with precision. The physics is known. The outcome at this level of detail is not fully resolved. What is certain is this: the sun is not a fixed backdrop. It is an evolving, aging object that has already transformed Earth's climate multiple times across geological history and will continue to do so at an accelerating pace as it approaches the later stages of its life. The comfortable, warm, yellow star, hanging 93 million miles away, approximately 150 million kilometers, is on a trajectory. That trajectory was set at the moment of its birth. Nothing we do, nothing any civilization anywhere in this solar system could ever do, alters the fundamental nuclear physics driving it forward. The question is not whether the sun will change Earth. It already has, continuously, for 4.5 billion years. The question is what the change looks like from here, and how much we actually understand about the stages still to come. The answer will surprise you. The core of the sun is a pressure negotiation that has been running for 4.5 billion years without interruption. On one side, gravity. The sun's own mass, approximately 2 times 10 to the power of 30 kilograms, or roughly 330,000 times the mass of the entire Earth, is perpetually attempting to collapse inward on itself. Every atom in the sun is being pulled toward the center with a force that, if unopposed, would crush the entire star into a dense, inert ball in a matter of minutes. On the other side, the outward pressure generated by nuclear fusion in the core, a continuous thermal shockwave pushing outward against gravity's grip. This balance, hydrostatic equilibrium, as astrophysicists call it, is what makes a star a star. It is not a static piece. It is an ongoing, dynamic standoff between two colossal forces, maintained continuously by the consumption of fuel. When the fuel runs low, the standoff ends. The sun has been converting hydrogen into helium in its core for 4.5 billion years, and in that time, the composition of its core has been changing in a way that has direct consequences for everything that follows. As hydrogen fuses, helium accumulates. Helium is heavier than hydrogen. Its nucleus contains 2 protons and 2 neutrons compared to hydrogen's single proton. As helium builds up in the core's density gradually increases. Protons in the remaining hydrogen are packed more closely together. This actually makes hydrogen fusion slightly more efficient, which is the precise physical reason why the sun's luminosity has been increasing gradually over its lifetime. The brightening is not incidental. It is a direct mathematical consequence of core composition changing over time. The rate of that brightening is approximately 1% per 100 million years, slow by any human intuition, unstoppable by any physical intervention. Now consider what happens when the hydrogen in the core is genuinely exhausted, not depleted to low levels, exhausted. When the concentration of hydrogen in the sun's central region drops below the threshold required to sustain fusion, the outward pressure from the core begins to fall. Gravity, which has been held at bay for billions of years, reasserts itself. The core begins to contract. What happens next is one of the most counterintuitive sequences in all of stellar physics, and it is worth understanding precisely because popular descriptions of it almost always get it wrong. The common assumption is that a dying star simply cools and fades. The sun runs out of hydrogen, the lights go out, the star grows cold. This is not what happens, not even close. The reality is almost the opposite. As the helium-rich core contracts under gravity, gravitational potential energy is converted into heat. The core gets hotter, not cooler, as it collapses. This is the Kelvin-Helmholtz mechanism, named for the 19th century physicists Lord Kelvin and Hermann von Helmholtz, who identified it before nuclear physics was even understood. Gravitational contraction releases thermal energy. The collapsing core heats up. That rising temperature spreads outward. The layer of hydrogen immediately surrounding the now inert helium core, hydrogen that was previously too cool to fuse, is now exposed to a dramatically higher temperature environment. It ignites. Hydrogen shell burning begins. A thin shell of hydrogen surrounding the dead helium core catches fire and begins fusing at a rate more intense than the core ever managed during its stable main sequence phase. The energy output surges, and that surge has nowhere efficient to go except outward into the star's outer layers. The outer envelope of the sun, the vast bulk of its volume that is not the core, responds to this sudden flood of energy by expanding. The expansion is gradual on a human timescale, but in stellar terms it is relatively rapid. Over the course of roughly 1 billion years, the sun will transition through what astronomers call the subgiant phase, its radius growing, its surface temperature dropping, its color shifting from yellow-white toward orange and then deep red. A star's surface temperature and its color are directly linked through blackbody radiation physics. Hotter surfaces emit bluer light. Cooler surfaces emit redder light. As the sun's expanding outer envelope cools, it reddens. The sun becomes eventually what is classified as a red giant. The numbers attached to that expansion are not abstract. At the peak of its red giant phase, the sun's radius is expected to reach somewhere between 100 and 200 times its current size. Today, the sun's radius is approximately 696,000 kilometers. Scaled up by a factor of 150, a conservative estimate, the sun would extend to a radius of approximately 104 million kilometers. Earth's current orbital distance from the sun is approximately 150 million kilometers. The margin between Earth's orbit and the edge of a maximally expanded red giant sun is, by these numbers, uncomfortably thin. Whether Earth is physically engulfed depends on factors that are still being actively modeled, including how much mass the sun loses through its stellar wind during the red giant phase, which affects the gravitational dynamics of Earth's orbit. Mass loss changes everything in orbital mechanics. As the sun sheds mass, and it will through an intensifying stellar wind in its later stages, the gravitational hold it exerts on the planets weakens. Weaker gravity means the planets spiral outward to larger orbits. Earth may migrate outward enough to survive physical engulfment. It will not, under any scenario, survive the thermal consequences. At the distances being discussed, with the sun radiating as a red giant, Earth's surface temperature would exceed several thousand degrees Celsius. The atmosphere would be stripped. The crust would partially melt. Whatever the exact orbital arithmetic resolves to, the Earth as a habitable world ends long before the sun's outermost layers reach it. The helium core, meanwhile, continues its own separate story. As the hydrogen shell burns above it, the helium core keeps contracting and heating. But helium fusion requires far higher temperatures than hydrogen fusion. While hydrogen fuses at approximately 10 million degrees Celsius in a stellar core, helium fusion, the process of fusing 3 helium nuclei into a single carbon nucleus, known as the triple alpha process, requires temperatures of approximately 100 million degrees Celsius, 10 times hotter. The core must contract and heat for an enormous period of time before those temperatures are reached. During this contraction, a strange quantum mechanical phenomenon takes over the core's physics: electron degeneracy. In an ordinary gas, pressure and temperature are linked. Heat a gas, it expands, the pressure rises, the temperature stabilizes. It is a self-regulating system. But as the helium core contracts to extreme densities, the electrons inside it are packed so tightly that quantum mechanics, specifically the Pauli exclusion principle, which forbids 2 electrons from occupying the same quantum state simultaneously, generates a pressure that is entirely independent of temperature. A degenerate electron gas does not behave like a normal gas. It cannot self-regulate. Heat it, and the pressure does not increase proportionally. The temperature can rise without limit, while the volume stays essentially fixed. This removes the natural thermostat. In a normal stellar core, a sudden increase in the rate of fusion would heat the gas would expand, the expansion would cool it, and the fusion rate would drop back to equilibrium. Automatic, elegant, stable. In a degenerate core, that feedback loop is broken. When helium fusion finally ignites at 100 million degrees Celsius in the degenerate core, the energy released heats the core further. But the pressure doesn't increase with temperature, so the core doesn't expand. The temperature rises, the fusion rate increases. The triple alpha process is extraordinarily sensitive to temperature, scaling with roughly the 40th power of temperature, meaning even small temperature increases produce enormous increases in fusion rate. More fusion, more heat, more fusion. A runaway. The result is the helium flash. In a fraction of a second, in some models, the peak energy release happens in under a second. The helium core releases energy equivalent to the entire luminosity of the Milky Way galaxy. The entire luminosity of a galaxy containing hundreds of billions of stars, released from a volume roughly the size of Earth in a moment. And almost none of it reaches the surface. The energy of the helium flash is almost entirely absorbed by the star's own outer layers. From the outside, from the perspective of any observer watching the sun at that moment, nothing dramatic is immediately visible. The star does not explode. It does not flash visibly. The energy is swallowed by the convective envelope above, and the star actually shrinks and dims slightly in the immediate aftermath as the core's degeneracy is lifted and the normal pressure-temperature relationship is restored. The runaway stops. Stability returns. But the sun is now a fundamentally different object. A star burning helium in its core, sitting on what astronomers call the horizontal branch of stellar evolution. The clock, however, is running faster now. Helium fusion is significantly less efficient than hydrogen fusion. The sun's helium-burning phase will last only approximately 100 million years, compared to the roughly 10 billion years of its hydrogen-burning main sequence lifetime. 100 million years sounds generous. It is 1/100th of the time the sun has already spent in its current stable state. The fuel is burning faster, the timescale is collapsing, and at the end of the helium-burning phase, the same sequence begins again. But the next step produces something the inner solar system has never encountered: carbon, oxygen, and a second, more violent expansion. The triple alpha process is one of the most improbable reactions in the known universe, and without it, none of this would exist. When helium nuclei fuse, they do not combine simply the way hydrogen nuclei do. Hydrogen fusion is, in relative terms, a direct transaction. 2 protons, some intermediate steps involving weak nuclear force interactions, and a helium nucleus emerges. The energy accounting is clean. Helium fusion is far more complicated, and the reason comes down to nuclear resonance, a phenomenon that, when physicists first worked through the mathematics in the early 1950s, revealed something so precisely calibrated that it stopped one of the most rigorous skeptics in the history of science cold. The problem with fusing helium is the intermediate step. 2 helium-4 nuclei, alpha particles, can collide and briefly form beryllium-8, but beryllium-8 is extraordinarily unstable. Its half-life is approximately 8 times 10 to the power of negative 17 seconds. That is 800 attoseconds. In that almost incomprehensibly brief window, a third helium-4 nucleus must collide with the beryllium-8 and fuse with it before it decays. The probability of this happening under ordinary circumstances is vanishingly small. For it to happen at a rate sufficient to power a star, the reaction needs a resonance, a specific excited energy state of the resulting carbon-12 nucleus that makes the fusion dramatically more likely. In 1952, the British astrophysicist Fred Hoyle predicted that this resonance state must exist, not because he had measured it, because carbon exists, because we exist. Because the universe contains carbon in sufficient abundance to build planets and biochemistry, Hoyle reasoned backward from the evidence of existence itself to the conclusion that nuclear physics had to permit it. His prediction was tested the following year by William Fowler's team at the California Institute of Technology. The resonance state was found exactly where Hoyle said it would be, at an energy level of approximately 7.656 million electron volts above the carbon-12 ground state. The Hoyle state, as it is now known, is one of the most precisely confirmed predictions in the history of nuclear astrophysics. Without that resonance, the triple alpha process would be so improbable as to be effectively impossible at stellar temperatures. Carbon would not accumulate in stellar cores. The universe would contain almost no carbon. No carbon means no organic chemistry. No organic chemistry means no life of any kind that we know of or can reasonably hypothesize. The nuclear energy levels of carbon-12 are not random. They are what they are. And what they are happens to permit the existence of everything that has ever lived. Inside the sun's core during its horizontal branch phase, helium is fusing through the triple alpha process into carbon-12 at temperatures of approximately 100 million degrees Celsius. Some of that carbon-12 undergoes a further reaction. It captures an additional helium-4 nucleus and becomes oxygen-16. The ratio of carbon to oxygen produced depends on the competition between these two reactions at the specific temperatures and densities present in the core, and that ratio is one of the quantities stellar physicists work hardest to pin down precisely, because it affects everything that follows in a star's evolution. Current best estimates suggest the sun's core will end the helium-burning phase with a roughly equal mixture of carbon and oxygen, though the exact proportion carries meaningful uncertainty. Helium burns faster than hydrogen. The horizontal branch phase lasts approximately 100 million years for a star of the sun's mass, roughly 1% of the main sequence lifetime. When the helium in the core is exhausted, the same sequence that ended hydrogen burning repeats itself, but now with a carbon-oxygen core contracting under gravity as helium burning migrates outward into a shell above it. Below the helium shell, the carbon-oxygen core contracts and heats. Above the helium shell, hydrogen shell burning continues. The star now has two active burning shells, hydrogen above, helium below, surrounding an inert, contracting core. Two simultaneous shell-burning sources feeding energy into the stellar envelope produce an instability. The outer layers expand dramatically, far more than during the first red giant phase. The sun enters what astronomers call the asymptotic giant branch, the AGB phase. And in this stage, the expansion is more extreme, the luminosity higher, and the behavior more erratic than anything in the first red giant phase. AGB stars pulsate. The outer envelope expands and contracts on timescales of hundreds of days, driven by complex interactions between the two burning shells and the convective outer envelope. These pulsations are not gentle oscillations. They are driven by opacity changes in the stellar atmosphere, specifically by how transparent or opaque the outer layers are to the radiation trying to escape through them. When the opacity increases, radiation pressure builds up and pushes the outer layers outward. When the layers expand and cool, opacity drops, radiation escapes more freely, and the layers fall back inward. The cycle repeats, building in amplitude over time. A star of the sun's mass on the AGB will swell to a radius somewhere between 200 and 500 times its main sequence size. At 500 solar radii, the sun's outer atmosphere would extend to approximately 350 million kilometers from its center, well past the current orbit of Earth and approaching the orbit of Mars. The surface temperature of these outer layers drops to roughly 2,000 to 3,000 Kelvin, cooler than the flame of an acetylene torch cooler than some classes of brown dwarfs. At those temperatures, atoms in the stellar atmosphere can combine into molecules. In carbon-rich AGB stars, carbon monoxide forms first, consuming all available oxygen, and the remaining carbon builds more complex molecules. In oxygen-rich AGB stars like the Sun is expected to become silicate and aluminum oxide dust grains condensed directly out of the cooling atmospheric gas. Dust, forming inside the outermost layers of the dying Sun. These dust grains are not trivial. They are the seeds of future solar systems. When light from the luminous AGB core strikes these newly formed dust grains, radiation pressure accelerates them outward. Dust drags surrounding gas with it. The result is a slow but continuous outflow of stellar material, the AGB wind, carrying dust and gas away from the star at velocities of 10 to 30 kilometers per second. For perspective, the International Space Station orbits Earth at approximately 7.7 kilometers per second. AGB stellar winds move faster than a spacecraft in low Earth orbit, continuously in all directions for millions of years. The mass loss during the AGB phase is substantial. A star the mass of the Sun is expected to lose between 40 and 50% of its total mass through stellar winds before the AGB phase ends. Nearly half of everything the Sun currently is, hundreds of thousands of Earth masses of gas and dust, will be dispersed into the surrounding interstellar medium over the course of the AGB phase. The solar neighborhood, currently populated by a thin distribution of interstellar gas and dust, will be filled with an expanding shell of material ejected from the dying Sun. Then comes the thermal pulse. As the helium shell above the carbon-oxygen core periodically reignites in brief, intense burning episodes, thermal pulses, a convective mixing event called dredge-up can carry freshly synthesized carbon from the burning shell into the outer convective envelope of the star. In more massive AGB stars, this carbon dredge-up transforms the star's surface chemistry from oxygen-dominated to carbon-dominated, turning it into a carbon star, one of the most chemically rich objects in the galaxy. For a star of the Sun's exact mass, the number of thermal pulses and degree of dredge-up is less certain, and this is an area of active research in stellar evolution modeling. The thermal pulses accelerate mass loss. Each pulse sends a pressure wave through the stellar envelope, amplifying the wind. In the final stages of AGB evolution, the mass loss rate increases dramatically. A phase astronomers term the superwind, during which the star can lose mass at rates up to 10,000 times higher than the current solar wind. The Sun today loses approximately 1.4 times 10 to the power of 14 kilograms per second through its solar wind. The AGB superwind can drive mass loss at rates millions of times higher. In the final thousands of years of the AGB phase, the star is shedding itself faster than at any previous point in its life. What is being shed is not just gas. It is processed material, atoms that were forged in the nuclear reactions of the star's interior, dredged up by convection into the outer layers, and then expelled into space. Carbon atoms that were helium nuclei 100 million years ago. Oxygen atoms synthesized in the triple alpha aftermath. Nitrogen produced by hydrogen burning in the CNO cycle. These elements are real. They are verifiable in the spectra of AGB stars observed across the galaxy right now, at this moment, by ground-based and space-based telescopes. The enrichment of the interstellar medium by AGB stellar winds is one of the primary mechanisms by which the galaxy builds its reservoir of heavy elements over time. The Sun, in dying, will seed the galaxy with the raw materials of future chemistry. But the AGB phase does not end quietly. The accelerating superwind strips away the outer envelope with increasing violence, and somewhere in the final stages, a transition happens that produces one of the most visually spectacular objects in astronomy. Something whose origin was debated for over a century, something whose physics was only fully understood in the second half of the 20th century. Something that the Hubble Space Telescope has revealed to be structures of almost impossible intricacy and beauty. The exposed core is about to turn the ejected envelope into a display unlike anything else in the observable universe. For most of human history, astronomers looking through telescopes at certain faint glowing patches of sky assumed they were looking at distant solar systems in formation, clouds of gas coalescing around newborn stars. The name given to these objects in the 18th century reflected that assumption. William Herschel, the German-born British astronomer who discovered Uranus in 1781, coined the term planetary nebula because these objects appeared as small, round, greenish disks in his telescope, superficially resembling the disk of a planet. The name was wrong from the beginning. Planetary nebulae have nothing to do with planets. They are the expelled outer envelopes of dying stars, illuminated by the ultraviolet radiation pouring from the exposed stellar core left behind after the AGB superwind has done its work. The misidentification persisted for nearly a century. It was not until the development of spectroscopy in the 19th century, the technique of splitting starlight into its component wavelengths to identify the chemical signatures of elements, that astronomers began to understand what planetary nebulae actually were. When William Huggins turned a spectroscope on the Cat's Eye Nebula in 1864, he did not see the continuous spectrum of a collection of stars. He saw discrete bright emission lines, the signature of hot, diffuse ionized gas. A cloud of gas glowing not by reflected light, but by its own emission, excited by intense radiation from a central source. The era of nebular spectroscopy had begun, and the true nature of these objects slowly came into focus over the following decades. What the spectroscope revealed was confirmed and deepened by a century of subsequent observation. A planetary nebula is not a random explosion. It is a structured, physics-driven transformation of stellar material, shaped by the interplay of multiple episodes of mass loss occurring at different velocities over different timescales during the AGB phase. The geometry emerges from the physics. The slow AGB wind moving at 10 to 30 kilometers per second builds up a large, roughly spherical shell of gas and dust around the star over thousands of years. Then, as the star transitions off the AGB and the outer envelope is fully stripped away, the exposed hot core, initially still surrounded by a thin layer of residual hydrogen, begins to heat up rapidly. The surface temperature of the exposed core rises in stellar evolution terms very quickly, from the cool temperatures of the AGB surface to temperatures exceeding 100,000 Kelvin within a few thousand years. As the surface temperature climbs above roughly 30,000 Kelvin, the core begins emitting copious ultraviolet radiation. At 50,000 Kelvin and beyond, the ultraviolet output is intense enough to ionize the surrounding ejected gas, stripping electrons from hydrogen and helium atoms in the expanding shell. Ionized hydrogen glows. When a free electron recombines with a proton to form a neutral hydrogen atom, it cascades down through the atom's energy levels, emitting photons at specific wavelengths. The dominant visible emission line of hydrogen, H-alpha, falls at a wavelength of 656 nanometers deep in the red part of the spectrum. Ionized oxygen emits strongly at 507 nanometers in the blue-green. Ionized nitrogen contributes additional red emission. The result is a structure that glows with colors that are not metaphorical or artistic interpretations. They are the direct, measurable spectral output of specific atomic transitions occurring in gas that was, 10,000 years earlier, part of the outer atmosphere of a star. Simultaneously, a fast wind develops from the now exposed hot core, moving at velocities of 1,000 to 3,000 kilometers per second, compared to the original slow AGB wind at 10 to 30. This fast wind slams into the previously ejected slow wind material, compressing it into a dense shell and sculpting the inner boundary of the nebula. The interaction between fast and slow winds, the interacting stellar winds model, developed primarily by Bruce Balick and Adam Frank in the 1980s and 1990s, explains the basic two-shell structure seen in many planetary nebulae and the origin of the bright inner rim visible in objects like the Ring Nebula in Lyra. The Ring Nebula, Messier 57, sits approximately 2,500 light-years from Earth in the constellation Lyra. It was discovered by the French astronomer Antoine Darquier de Pellepoix in 1779. 2 years before Herschel coined the term planetary nebula. Its central white dwarf, the exposed stellar core, has a surface temperature of approximately 120,000 Kelvin, among the hottest stellar surfaces known. The ring of glowing gas surrounding it spans approximately 1 light-year in diameter. That single light-year represents the material shed by the progenitor star during its AGB phase. Gas and dust that was once the star's outer atmosphere, now illuminated from within by the nuclear fire of the exposed core. 1 light-year of former stellar atmosphere, expanding outward at roughly 20 kilometers per second into the surrounding interstellar medium. The shapes of planetary nebulae are astonishing in their variety, and that variety is information. A perfectly spherical nebula indicates a single star system with no major asymmetries in the mass loss process. Bipolar nebulae, those with two lobes projecting in opposite directions, like the Butterfly Nebula or the Ant Nebula, indicate that the progenitor star had a binary companion, or that rapid rotation created an equatorial density enhancement that collimated the stellar outflow into jets. Multipolar nebulae with 4 or more lobes suggest even more complex interaction histories. The morphology of a planetary nebula is a fossil record of the dying star's final millennia, a three-dimensional archive of every episode of asymmetric mass loss, every binary interaction, every magnetic field configuration that shaped the outflow. The Hubble Space Telescope, launched in 1990 and operational through multiple servicing missions, transformed the study of planetary nebulae in a way that cannot be overstated. Ground-based images showed glowing ovals and rings. Hubble's images showed knots of dense gas called cometary globules, fine-scale filaments threading through ionized shells, nested concentric rings recording individual thermal pulse episodes from the AGB phase, like tree rings recording annual growth, and central cavities sculpted by the fast stellar wind with a precision that ground-based instruments had never been able to resolve. The Helix Nebula, NGC 7293, one of the closest planetary nebulae to Earth at approximately 650 light-years, revealed in Hubble imaging a structure of approximately 20,000 cometary globules arranged in a vast torus around the central white dwarf, each globule a dense knot of molecular gas with an ionized head pointing toward the central star and a long molecular tail pointing away from it. 20,000 individual structures, each one a product of the same instability processes that operate at the interface between the ionized inner nebula and the neutral molecular outer shell, each one containing enough gas to fill the inner solar system, each one invisible from Earth without the resolving power of space-based observation. The central white dwarf in all of these systems is what remains of the stellar core after the hydrogen and helium envelopes have been expelled. For a star of the Sun's mass, the white dwarf that remains will have a mass of approximately 50 to 60% of the current solar mass, the rest having been expelled in winds and the nebula itself. Its radius will be comparable to that of Earth, roughly 10,000 kilometers. The same mass as 50 to 60% of the Sun, compressed into a volume the size of a rocky planet. The density that results is almost beyond compression into ordinary language. A teaspoon of white dwarf material, approximately 5 cubic centimeters, would weigh several tons on Earth's surface. The electron degeneracy pressure supporting the white dwarf against further gravitational collapse is not a nuclear process. There is no fusion happening inside a newly formed white dwarf. It is supported purely by the quantum mechanical resistance of electrons to being compressed into the same quantum state, the same Pauli exclusion principle that governed the degenerate helium core during the helium flash, now operating at the scale of the entire stellar remnant. Without a new energy source, the white dwarf can only cool. It radiates its stored thermal energy into space over billions of years, first white-hot, then yellow, then orange, then red, dimming continuously on a timescale far longer than the current age of the universe. The universe is approximately 13.8 billion years old. The cooling time for a white dwarf to reach a completely cold, dark state, a black dwarf, exceeds 10 to the power of 15 years. No black dwarf yet exists anywhere in the observable universe. The universe is not old enough to have produced one. The planetary nebula itself lasts only a brief time by astronomical standards. The ionized gas disperses into the interstellar medium within approximately 10,000 to 30,000 years of the nebula's formation. The ultraviolet output of the central white dwarf fades as it cools below the ionization threshold. The glowing shell becomes invisible, absorbed into the general population of interstellar gas and dust. What remains after the light fades is the white dwarf, cooling silently in the dark, carrying the compressed memory of everything the star ever was. Somewhere in the galaxy right now, stars are doing exactly this. not metaphorically, observationally. The galaxy contains an estimated 20,000 to 50,000 planetary nebulae visible at any given time, representing the overlap between the brief planetary nebula phase and the timescales of stellar evolution across a galaxy of hundreds of billions of stars. Each one is a real-time record of a transformation that the Sun will undergo, not as a possibility, as a certainty embedded in the laws of nuclear physics that have not changed and will not change. The question that remained unanswered for decades, the one that produced the sharpest disagreement among stellar physicists working on this problem, was whether the Sun, specifically, would produce a planetary nebula visible from a distance. The answer, as of a landmark study published in 2018, is surprising, and it changes what we thought we knew about the minimum stellar mass required to produce a detectable nebula. That answer reframes everything that follows. The 2018 study that changed the answer to whether the Sun would produce a visible planetary nebula came from a team led by Quentin Parker at the University of Hong Kong, working with colleagues at the University of Manchester. The conclusion was not based on new observations of the Sun itself. The Sun is nowhere near the end of its life, but on a fundamental recalibration of the relationship between stellar mass, stellar temperature at the end of the AGB phase, and the brightness of the resulting nebula. The previous consensus held that stars at or below the Sun's mass would transition off the AGB too slowly. By the time the exposed core heated up sufficiently to ionize the surrounding ejected shell, the shell would have dispersed too far into the interstellar medium, becoming too diffuse and too faint to detect. A detectable planetary nebula, the old models suggested, required a star with at least twice the Sun's mass. The Sun, at one solar mass, would quietly shed its envelope and produce a white dwarf surrounded by a ghost of gas too faint to observe from any meaningful distance. The 2018 recalibration overturned this. The new stellar evolution models incorporated improved data on how stellar remnant cores heat up during the post-AGB transition. Specifically, updated empirical relationships between the initial mass of a star and the mass of the white dwarf it produces, derived from observations of white dwarfs in star clusters of known age and composition. The revised models showed that stars as low as approximately 1.1 solar masses, close enough to the Sun's mass to be directly relevant, can produce planetary nebulae bright enough to be detected at the distances of other galaxies in the local group. The Sun, according to this revised picture, will produce a planetary nebula, faint by the standards of more massive progenitors, but real and detectable. The peak brightness of the Sun's future planetary nebula will occur approximately 1,000 years after the post-AGB transition begins. The brief window when the central white dwarf is hottest, its ultraviolet output is greatest, and the ejected shell is at the optimal density for efficient ionization and emission. During that window, the nebula's absolute brightness in the green oxygen emission line at 507 nanometers will reach levels comparable to the faintest planetary nebulae observed in nearby galaxies today. The Andromeda Galaxy, Messier 31, is approximately 2.5 million light-years away, and even at that distance, a bright planetary nebula is detectable with modern instruments. The Sun's will not rank among the brightest. It will not be among the most spectacular. But it will exist, glowing for a few thousand years before the white dwarf cools below the ionization threshold and the light fades permanently. A few thousand years out of 10 billion. A flash by any measure. What remains after that flash is the white dwarf, and its properties are known with considerable precision from first principles and from the observed population of white dwarfs in the Milky Way. The Sun's white dwarf remnant will have a mass of approximately 0.54 solar masses, based on the initial to final mass relationship derived from cluster observations. Its initial surface temperature will be on the order of 100,000 to 150,000 Kelvin. Its radius will be approximately 5,000 to 7,000 kilometers, smaller than Earth, roughly comparable to a large rocky planet. Everything that the Sun currently is, its volume, its outer layers, its decades and centuries of gradual luminosity increase, will be compressed into an object smaller than any planet in this solar system, supported not by nuclear fire, but by the quantum mechanical stubbornness of electrons refusing to share quantum states. The cooling of a white dwarf follows a well-understood physical trajectory. In its earliest phase, while the surface is still extraordinarily hot, The white dwarf radiates primarily in the ultraviolet and soft X-ray, pouring energy into the surrounding nebula, and then, after the nebula disperses, simply into empty space. As it cools through 100,000 Kelvin toward 50,000, it transitions from ultraviolet dominant to emitting primarily invisible blue-white light. At 20,000 Kelvin, a temperature the sun's white dwarf remnant will reach after several hundred million years of cooling, it sits in a region of the Hertzsprung-Russell diagram called the ZZ-CT instability strip, where the partial ionization of hydrogen in the outer envelope drives pulsation modes that make the white dwarf oscillate in brightness on timescales of minutes to hours. These pulsations are not catastrophic. They are the stellar remnant ringing like a bell, its outer layers responding to the changing opacity structure of a cooling atmosphere. Asteroseismology of white dwarfs, the study of these pulsation modes, allows astronomers to probe the internal structure of white dwarfs in ways that direct observation cannot. The frequencies of the oscillation modes encode information about the thickness of the hydrogen and helium layer structure, the mass of the carbon-oxygen core, and the presence or absence of crystallization in the deep interior. At sufficiently low temperatures, the carbon and oxygen ions in the white dwarf core begin to arrange themselves into a crystalline lattice, a body-centered cubic structure, releasing latent heat as they do so. This crystallization process, first predicted theoretically in the 1960s by David Kersnitz and subsequently by Edwin Salpeter and others, was confirmed observationally in 2019 by a study using Gaia spacecraft data. Gaia detected a statistical pileup of white dwarfs at a specific luminosity on the Hertzsprung-Russell diagram, precisely the luminosity predicted for the crystallization stage, confirming that the cores of old white dwarfs are, in the most literal sense, giant crystals of carbon and oxygen floating in space. The sun's core, in its final form, will be a crystal, not metaphorically, not poetically, a crystal of carbon and oxygen, approximately the size of Earth, with a surface temperature gradually declining over billions of years toward the ambient temperature of the universe. The cooling slows as the temperature drops. The specific heat of the crystalline interior retains thermal energy, and the timescale for a white dwarf to cool to a completely dark, inert black dwarf exceeds the current age of the universe by many orders of magnitude. At the present age of the universe, the oldest white dwarfs, remnants of the first generation of stars massive enough to have completed their evolution within 13.8 billion years, have cooled to surface temperatures of approximately 3,000 to 4,000 Kelvin. Their luminosity is approximately 1/10,000th of the current sun's luminosity. They are red, dim, and ancient, but still not cold. The solar system that surrounds the white dwarf will be a transformed place. The inner planets, Mercury, Venus, and almost certainly Earth in any thermally meaningful sense, will not survive the red giant and AGB phases intact. Mercury and Venus will be engulfed or ablated. Earth's fate depends on orbital migration driven by solar mass loss, but its surface and atmosphere will be unrecognizable long before any physical engulfment. The outer solar system, Jupiter, Saturn, Uranus, Neptune, will survive. Their orbits will expand as the sun loses mass, pushing them to larger orbital radii. The Kuiper belt and the Oort cloud will be partially disrupted, with a fraction of their cometary bodies being ejected into interstellar space by the changed gravitational landscape, and others being driven onto new orbits that send them inward through the now quiet inner system. Jupiter and Saturn, orbiting a white dwarf 1/2 the mass of the current sun, will settle into new, wider orbits, Jupiter migrating from its current 5.2 astronomical units to somewhere between 7 and 8 astronomical units, Saturn from 9.5 to approximately 13 or 14. These gas giants will persist essentially unchanged in their bulk composition for timescales comparable to the age of the universe. Their existence around a cooling white dwarf will not be unique. White dwarfs with planetary companions have already been detected. White dwarf atmospheres show contamination by heavy elements, silicon, iron, calcium, magnesium, that cannot have been synthesized in the white dwarf itself and must have been accreted from disrupted rocky bodies in the surrounding system. Tidal disruption of asteroids and minor planets by the white dwarf's gravity delivers this material to the stellar surface, where it sinks rapidly through the dense atmosphere on timescales of days to millions of years depending on the atmospheric temperature and composition. The white dwarf is still consuming the debris of its own former solar system. This is not a future scenario projected from models alone. It is happening now, around white dwarfs observable today. The Spitzer Space Telescope and subsequently the James Webb Space Telescope have detected infrared excesses around white dwarfs consistent with circumstellar dust disks, the remnants of tidally disrupted minor planets spiraling inward. Spectroscopic analysis of the polluted white dwarf atmospheres reveals the bulk compositions of the accreted bodies. Rocky material rich in magnesium, silicon, and iron, consistent with the composition of differentiated rocky bodies. Asteroids, minor planets, perhaps the remnants of fully formed terrestrial worlds. What the Sun will eventually do to the remnants of its own asteroid belt, and perhaps to the remnants of Earth itself, is not hypothetical inference. Astronomers are watching it happen around other stars right now, in real time, with instruments sensitive enough to read the chemical autobiography of destroyed worlds in the spectrum of a cooling stellar remnant. The Sun will eat what remains of its solar system, slowly, passively, over billions of years, as gravitational dynamics destabilize the orbits of surviving small bodies and send their debris raining down onto the white dwarf surface. The iron in those remnants will flash freeze into the white dwarf atmosphere and sink below the surface in the time it takes a human civilization to rise and fall. And the white dwarf, growing colder and dimmer by imperceptible fractions each millennium, will carry on cooling toward a darkness that the present universe has not yet had time to produce anywhere. The silence of that cooling is not the silence of nothing. It is the silence of physics fully expressed, every law obeyed, every process completed, every gram of available nuclear fuel spent across a lifetime of 10 billion years. The light we see when we look at the Sun today is 10 billion years old in its making. It is the product of a nuclear contract written at the moment of the Sun's formation, a contract whose final clauses we have now read in full. There is one question left. Not about the Sun's death. About what that death means for the only planet that ever looked up and wondered what was happening. Every atom of calcium in every bone of every human being alive today was forged inside a star that died before the Sun was born. This is not a metaphor. It is a statement of nuclear physics and stellar evolution that can be traced, element by element, through the observable chemistry of the galaxy. The calcium in bone, the iron in blood, the oxygen drawn into lungs with each breath, the carbon forming the backbone of every organic molecule in every living cell. None of it was present in the universe at the moment of the Big Bang. The Big Bang produced hydrogen, helium, and trace amounts of lithium. Everything else, every element in the periodic table heavier than lithium, was manufactured inside stars, through the same nuclear processes that have been operating inside the Sun for 4.5 billion years, and through the catastrophic events that end a massive star's life, and through the slower, gentler processes of low-mass stars shedding their outer envelopes across the galaxy in stellar winds and planetary nebulae. The Sun is a second-generation star, at minimum. The cloud of gas and dust from which it formed, the solar nebula 4.5 billion years ago, was not primordial material. It was pre-enriched by the deaths of earlier stars. The iron in Earth's core was forged in the core collapse of a massive star that exploded as a supernova before the Sun existed. The carbon in every organic molecule on Earth passed through the triple alpha process inside some earlier red giant. The oxygen in the oceans was synthesized in stellar interiors and expelled into the interstellar medium before it ever became part of a water molecule on this planet. The Sun, when it dies, continues this process. The carbon and oxygen expelled during the AGB phase, the enriched gas shed during thermal pulses, the material driven outward in the superwind, all of it enters the interstellar medium and becomes available for the next generation of star formation. The galaxy's inventory of carbon, nitrogen, and oxygen, the elements most critical to organic chemistry, is built up over billions of years precisely through the cumulative deaths of stars like the Sun. A galaxy that has been forming stars for 10 billion years has been recycling stellar material through this cycle for 10 billion years. The interstellar medium today is fundamentally different in chemical composition from the interstellar medium of the early universe, and the difference is entirely the product of stellar evolution and stellar death. The Sun's eventual white dwarf will carry approximately half the Sun's current mass. The other half, expelled across the red giant, AGB, and planetary nebula phases, returns to the interstellar medium. Some of that material will remain as diffuse gas for billions of years. Some will be swept up in the shock waves of nearby supernova explosions, compressed into dense molecular clouds, and triggered into forming new stars. Some may eventually become part of a new solar system, a new planetary system forming around a star not yet born, orbiting a galaxy that the Sun will never see in its current form. The timescales involved in that recycling are enormous. From the dispersal of a planetary nebula to the formation of a new star from the enriched interstellar medium can take hundreds of millions to billions of years. The galaxy does not rush. It has been at this process since shortly after its formation, approximately 13 billion years ago, and it will continue far beyond any timescale that the current inventory of stars can illuminate. Within those timescales, Earth's position in this story is geometrically precise and physically unambiguous. Earth formed from the solar nebula 4.5 billion years ago. It has been the beneficiary of the Sun's stable luminosity throughout that entire period, a period of time that turns out to be almost exactly the right duration for complex life to arise, evolve, and develop the cognitive capacity to reconstruct the physics of what is happening around it. The Cambrian explosion of complex animal life occurred approximately 540 million years ago. The development of the nervous system, of eyes, of locomotion, of predation, of the ecological complexity that makes a biosphere robust, all of it unfolded under a sun stable enough to permit it. The 1 billion year habitability window remaining before solar brightening makes the surface untenable for complex water-dependent life represents roughly twice the entire history of animal life on Earth. It is not a generous margin. It is not a negligible one. What happens to life on Earth, or to whatever intelligence exists on or near this planet in the deep future, is a question that physics does not answer. Physics describes what the Sun will do. It describes the timescales with precision. It does not describe what cognitive systems will exist within those timescales, what technologies they may develop, whether any relocation of biological or technological civilization to other environments within or beyond the solar system is physically achievable or pursued. These are questions that lie in domains, biology, cognition, technology, where the uncertainties compound so rapidly over geological timescales that no scientific statement of any useful precision is available. What is available is the physical context, and the physical context is this: the transformations the Sun will undergo are not unique to the Sun. They are standard stellar evolution for a G-type main sequence star of approximately 1 solar mass. Every such star in the galaxy follows this path. The Milky Way contains approximately 200 billion stars, of which a substantial fraction are G, K, and M-type stars capable of supporting liquid water on planets in their habitable zones for timescales comparable to or exceeding Earth's current age. If the question of life's origin and evolution has a general answer rather than an Earth-specific answer, if the conditions that produce life here are sufficiently common across the galaxy, then this story of stellar aging and planetary transformation is not one story. It is a template repeated across hundreds of millions of stellar systems, each on its own timeline, each at a different stage of the same sequence. Stars currently in their red giant phase in this galaxy have planets. Some of those planets were, 1 billion years ago, temperate, potentially habitable worlds orbiting stable main sequence stars. The question of whether any of them harbored life, and what happened to it as the parent star expanded, is not answerable with current observational technology. It is, however, a physically legitimate question, grounded in exactly the same stellar physics that governs the Sun. The study of stellar evolution is, among other things, the study of the finite duration of the conditions that make complex chemistry and biology possible. Every stable main sequence star is a temporary phenomenon, a balance between gravity and nuclear pressure that is maintained only for as long as the fuel lasts. The Sun's 10 billion year main sequence lifetime is neither unusually short nor unusually long by the standards of the galaxy's stellar population. Low-mass red dwarf stars, which constitute the most common type of star in the galaxy, fuse hydrogen so slowly that their main sequence lifetimes extend to trillions of years, far beyond the current age of the universe. Massive blue stars burn so intensely that they exhaust their hydrogen fuel in tens of millions of years, ending their lives in the core collapse supernovae that forge the heaviest elements. The Sun sits in between, a middleweight star, a middle-aged star, on a timeline that happens to be long enough for the only confirmed example of complex intelligence in the universe to have arisen and looked outward. The ability to reconstruct the Sun's entire life history, from the collapse of the solar nebula 4.5 billion years ago through the main sequence phase, the red giant, the AGB, the planetary nebula, the white dwarf, and the long cooling toward a darkness the universe has not yet produced. From observations of other stars at different stages of the same sequence, from laboratory nuclear physics, from spacecraft observations of white dwarf atmospheres, from the Gaia mission's precise measurements of stellar positions and luminosities, is one of the more extraordinary achievements of observational and theoretical science. No instrument has ever directly observed a star complete this entire sequence. No civilization has existed long enough to watch it happen in real time. But the physics is sufficiently well understood, the observations of stellar populations at every stage sufficiently complete, and the laboratory measurements of nuclear reaction rates sufficiently precise that the trajectory is known. Not guessed, not extrapolated loosely. Known in the sense that scientific knowledge means something reproducible, testable, and confirmed by independent lines of evidence converging on the same answer. The Sun will die. In dying, it will give back everything it borrowed from the interstellar medium across 10 billion years of nuclear burning, returning carbon, oxygen, and nitrogen to the galaxy for the next generation of stars and the next generation of worlds. The light that reaches Earth today left the Sun approximately 8 minutes and 20 seconds ago, having spent up to 100,000 years diffusing outward from the core where it was produced. Each photon is the product of a nuclear reaction involving hydrogen nuclei that fused before any complex life existed on this planet. Each one is the last leg of a journey that began in the core of a star at a temperature of 15 million degrees Celsius, traveled outward through a radiation zone where progress is measured in millimeters per year, convected to the surface, and then crossed 150 million kilometers of vacuum in 8 minutes and 20 seconds to warm a surface, drive photosynthesis, and make a biosphere. The Sun is not background. It is the story. The warming of the young Earth, the brightening over geological time, the eventual reddening and expansion, the loss of the oceans, the planetary nebula lasting a few thousand years in the dark, the cooling crystal of the white dwarf settling toward a silence the universe has not yet reached. It is one continuous physical sequence, governed by the same 4 fundamental forces that govern everything else, running on the fuel that was loaded into the solar nebula 4.5 billion years ago and will be fully spent 5 billion years from now. The carbon that built the first living cell on Earth was inside a star before it was inside anything alive. The carbon that exists in every living thing today will be inside a star again.